What's up, guys? This is Jahangir from MedPorium, and today we're going to be talking about acids and bases in water. We're also going to be talking about how to calculate pH, pOH, and all that fun stuff. So first, we want to talk about water, because water is classified as being amphoteric. So amphoteric. So amphoteric is basically water's ability to act as a acid and base. So what do I mean by this? How water can act as an acid and base? Well, water, H2O, can turn into hydroxide, or H2O can turn into hydronium. So this is water's ability to act as an acid and a base, whereas over here, water is acting as an acid because it is donating a hydrogen, and this is our conjugate base. While over here, water is acting as a base, and hydronium is a conjugate acid because the water over here is accepting a hydrogen. So remember, this is the action. When we're comparing hydrogens, we have an addition of hydrogen, so this water is going to be our base. So remember, look at the action, and that is our sort of whatever the reactant is. So now that we know that, let's talk about the autoionization of water. So autoionization of water, and that's basically the production of these hydroxides and these hydroniums. So if we just scroll down here a little, so when we're talking about autoionization, we're sort of, if you want to write it down, it's sort of looking like this. So we have two H2Os, and that goes to hydronium and hydroxide. So this is what autoionization of water looks like, and it is a transfer of protons, which creates our hydronium over here and hydroxide, so creating that H3O plus and OH minus. So this is autoionization of water, and it's important to know that this is in equilibrium. So this process can occur by the reactant side, product side, because both products and reactants the rate of those are both similar, which is why they're in equilibrium. And one way to basically show the autoionization of water is Kw. This W is really for the autoionization of water. This W is specifically for autoionization of water, and that would be H3O plus. This is kind of like the rate of the ionization of water. And we have OH minus. So further on in these videos, you're going to see some things like Ka or Kb and stuff like that. And these bottom letters right here really symbolize what we're actually talking about. This is what our Kw pretty much looks like. And you could also write it as, you can think of Kw as hydrogen ions and OH. Now, most of the time in reactions, you're going to see these hydroniums being produced, for example, with HCl. With hydrochloric acid in a solution, it is going to turn into hydronium and Cl minus. So usually you're going to see a production of hydronium, but you will also see these H pluses. Maybe the problem might give you the concentration of hydrogen, things like that. So now that we know that part of autoionization, now let's look at what this actually equals. So in pure water, the Kw is going to equal 1.0 times 10 to the negative 14th power. Now this is assuming that the reaction in pure water occurs at 25 degrees Celsius. Now since this hydronium times the hydroxide equals 1.0 times 10 to the negative 14, then the hydronium and the hydroxide equals 1.0 times 10 to the negative 7, assuming this is in pure water, and it is at 25 degrees Celsius, which should be our standard temperature. So this is what is pretty much given as our Kw, and that's what we know from this equation knowing that Kw equals 1.0 times 10 to the negative 14. And over here, this is going to be 1.0 times 10 to the negative 7 molars. Now, another thing to know is that the concentration of H3O plus, when that equals the concentration of hydroxide, our pH is neutral. Now, one thing you have to know about pH is if we have a higher pH, that means that we have less hydrogen ions. So pH is really characterized by these hydrogen ions, and let me actually change the color. So pH is characterized by having an accumulate of hydrogen ions, or just looking at how many hydrogen ions we have. If we have a lot of hydrogen ions, we are going to have a low pH. But if we have a low amount of hydrogen ions, maybe we even have hydroxide, then we're going to have a high pH. So pH really depends on the hydrogen concentration, and more specifically, our hydronium concentration. Now, if we have a higher concentration of hydronium compared to hydroxide, then obviously we are going to be more acidic. And if we have a concentration of hydroxide that is greater than hydronium, then we are going to have a basic solution. So hopefully that makes sense in the fact that pH really depends on these hydroniums or just hydroxide, these protons in general. And if we have a higher amount of those, it's more acidic. If we have a lower amount of those, more hydroxide, then we're going to become more basic. So let's break down a practice question, and let's just say the question says calculate the hydroxide concentration, and I'll just put just calculate hydroxide when our hydronium H3O plus equals 5.0 times 10 to the negative, and that should be 4 molars. So this is our question right here. Calculate the concentration of hydroxide when hydronium concentration equals 5.0 times 10 to the negative 4. So pause this video and try to see if you can solve this on your own. Now to solve this, I'll give you guys a little bit of a hint. Just know that Kw equals 1.0 times 10 to the negative 14, and then try to solve that. So if you tried solving that, you know that our Kw equals the concentration of hydronium times the concentration of hydroxide. Knowing that, you also know that Kw is 1.0 times 10 to the negative 14, and it's given that the hydronium is 5.0 times 10 to the negative 4 molars, and we're trying to find hydroxide concentration. So that's pretty much basic algebra, where we divide this part over here. So let me just copy paste this. We divide it by 5.0 times 10 to the negative 4, and do the same thing on the left side. And once we do that, we can just basically cancel this stuff out, because we know that this is going to equal OH, and when you solve that, you should get 2.0 times 10 to the negative 11 molars. And if you actually want to check that, we could do 5 times 10 to the negative 4, and whatever that is, and 2 times 10 to the negative 11, multiply those together, and we get 1.0 times 10 to the negative 14. So you can check your answer by just plugging in 2.0 times 10 to the negative 11 over here, and multiplying that by 5.0 times 10 to the negative 4 molars, and that gets us our answer of 1.0 times 10 to the negative 14. So we obviously know that using Kw to our advantage can help us solve these type of questions. But now, my question now is this solution acidic or basic? So just to give you guys a little bit of hint on that, remember these sort of things that we talked about, where if hydronium is greater, then we have acidic, and if hydroxide is greater, then we have a basic solution. So pause this video and try to find out if this solution is acidic or basic. So if you said this solution is acidic, You are correct, because the hydronium concentration, 5.0 times 10 to the negative 4, that number is greater than our hydroxide concentration, which lets us know that this is an acidic solution. So now let's talk about pH versus pOH. And there's two equations we need to know. So pH is going to equal negative log the concentration of hydronium, and it could also equal the negative log of our hydrogen plus concentration. And let me just move this over here. And let me change the color real quick. And pOH is going to equal negative log of our hydroxide. So those are two very important equations you just need to know in order to solve, for example, what is the pOH given a concentration of hydroxide, or what's the pH given the concentration of hydrogens. So these equations really come into play when you're trying to solve those type of questions. Now, just as another reminder, pH depends on the amount of hydrogen ions in the solution. If we have more hydrogen ions, we have a lower pH. If we have a lower amount of hydrogen ions, we have a higher pH. So pH depends on these hydrogen ions, and one of the things you have to know is that pH, so pH plus, and let me just change my color to white over here, so plus pOH over here, this is going to equal 14. So these are three of the main equations you just have to know, and you just really have to memorize these, or if your professor gives it on a formula sheet, then you really don't have to memorize it, but you just have to memorize these equations right here in order to solve understanding the pH given a specific concentration or given the pOH, things of that nature. So another thing to know is that if you're trying to solve, and let's say you're trying to solve the concentration of hydroxide given pOH, this negative log, that inverse of that, all you really have to do, and let me actually move this over here to the right. So when you're trying to find the concentration of hydroxide given pOH, to isolate this negative log, first you divide by -1, divide by -1, and that should just make this pOH negative. So we make that pOH negative, and we do 10 to the power of 10 to the power of. That cancels out the log, so then the concentration of hydroxide will equal 10 to the power of our negative pOH. And same thing for pH, where when we want to isolate that log, that negative log, first we change our pH to negative, then put it to the power of 10. Alright, so now that we know these equations, now let's go through a practice problem real quick. And our practice problem is asking us, what is the pH when our hydroxide concentration is 5.4 times 10 to the -5 molars. So obviously we need to use our equation over here, or actually I actually just changed that equation. So let me rewrite our pOH equation. So our pOH equation is going to be pOH equals negative log of our hydroxide concentration, and we're given our hydroxide concentration, so let's put that in the calculator real quick. So negative log of 5.4 times 10 to the -5 will get us 4.27. So I just rounded up there. So let's do negative log, and if we put this concentration in there, so I'll just put copy paste. So we put this concentration in there, and that negative log is equal to our pOH, and that equals 4.27. So we know that our pOH is 4.27. Now what? Well, we use this equation over here. pH plus pOH equals 14. I'm just going to scroll down over here. And we know our pOH. So it's just going to be, let me copy paste this. It's going to be pH plus 4.27, and that will equal 14. Let me copy paste that. So that will equal 14. Now all we have to do is just basic algebra, and when we do that, we're just subtracting 14 minus 4.27, and that gets us 9.7, I believe that's 9.73. Let me check real quick. 14 minus 4.27. Yeah, 9.73, and that is our pH. And also, one other thing to note is that anything above the pH of 7, so anything above pH of 7 is going to be basic, but anything below pH 7 is going to be acidic. Now, another word for basic is also alkaline, but this is something you have to realize, where our equilibrium pH, or the pH, or just neutral pH, where our hydronium ions or hydronium concentration equals our hydroxide concentration, then that is when we're at a pH of 7, because it's neutral. But if we have a pH greater than 7, it's going to be basic. If we have a pH less than 7, it's going to be acidic. So now, knowing all of that, there are some more things you have to memorize, not just only those equations, but you have to memorize all these strong acids, or at least the main strong acids. And these include H2SO4, we also have HI, then we have HBr, HNO3, HCl, HClO3, and HClO4. So these are our main strong acids, and you might be wondering, well, how am I supposed to memorize all of them? Well, there's a memory trick that you could use, and it is called the So I brought no clothes. So here's just an acronym you can use to memorize the strong acids. It's So I brought no clothes. So the So is our sulfite or sulfate. I kind of forgot my polyatomic ions, but I for our iodine, Br, brought for our Br, NO for our NO3 over here, and clothes for our Cl. But you do have to memorize ClO3 and ClO4. But here's just the easy way to memorize it. So I brought no clothes, and that is strong acids. And maybe you could even memorize it as I spilled acid on my clothes, so I brought no clothes. You could use some different ways to memorize these, but here's one way that I like to memorize the strong acids. And like I said, you guys kind of have to memorize these, and in many of the practice problems, they might give you this H2SO4 and just in a chemical formula, and you just have to know if it ionizes completely, because strong acids will always ionize completely. That's what makes them strong. So now that we got strong acids out of the way, let's talk about our strong bases. So I'll just put strong bases. And remember, strong bases, similar to acids, must ionize completely. It's what really makes them strong. And strong bases are a little bit more easy to memorize because they include group 1 and group 2 elements. So if you just look at the periodic table and you know where group 1 and group 2 elements are, then you're perfectly fine with understanding which ones are strong bases. But for group 1, we go from lithium hydroxide, then we have sodium hydroxide, we have potassium hydroxide, I don't know this one, RBOH, and CSOH. So that's our group 1 strong bases. And group 2, we have calcium hydroxide, I believe that's how you say it. We have SROH2, and we have BaOH. So these are our strong bases, obviously since, because they ionize completely, which is what makes them strong. And what these ionize to is Li plus OH minus. And these are all just going to be the same but different element, not just Li. And over here it's going to be Ca2 plus 2OH minus. Same thing for all of these. And like I said, you just have to memorize these strong acids and also the strong bases. Hopefully that helps you understand pH, POH, strong acids, strong bases, as well as understanding auto-ionization of water. And as always, a Pomodoro a day will make you a doctor someday. I'll see you guys in the next one.